continuing where I left, and we were discussing, finding the area of an ellipse using trigonometric substitution, and why the range should be from 0 to pi over 2, because we'd find the area in the first quarter, and the x coordinate goes from 0 to a. And by the time x coordinate goes from 0 to a or a to 0, the angle theta goes from 0 to pi over 2, right, in the first quadrant. And this is the substitution, okay? And let's now go back to writing the area, okay? And this expression for, y, right? The y equals b over a under root a square minus x square we had obtained earlier, and we are integrating that right now, okay? And how are we integrating? Oh, not triangle. Okay, so we are I'm sorry, I was thinking to myself, what we are integrating here is the area of this small, this rectangle. When the angle is theta, the area of that rectangle would be x coordinate times y coordinate. The area is xy, right? Okay, and xy, but we have expressed that xy in terms of, oh, okay, all right, not like that. You can take a rectangle here also, right? Okay, xy, but y has been expressed in terms of, so here this will be y, this small will be x, and the area would be expressed as xy. No, not xy. I mean dxy. Okay, not the area of the rectangle at the beginning or the end. Let's take the area of the rectangle of a strip in between. Okay, if I'm somewhere here, let's say, here, the strip is dx and the height is y, and area of that rectangle is y dx, right? Length into width, and you are integrating that from dx. So x goes from 0 to a. You are integrating that from 0 to a. Okay. But as that happens, as x goes from 0 to a, how am I expressing that? X goes from 0 to a, and it's y dx, but that y is this. So we get that expression, and we are multiplying that by 4 because there are 4 quarters, of that ellipse. Right now I'm thinking how, okay, so we, in the previous page we discussed, when x is 0, sine theta is 0, and when x is a, theta is pi over 2 because sine theta is 1. That is purely algebraic, like, derivation of that angle. But I also want to see that in the diagram, okay? That is what I'm trying to, I'm struggling here right now. When x is 0, we are at the origin. When x is a, we are here. So what theta are we talking about here? The theta is it the angle made with the x-axis? or is it the angle made with the y-axis? Because looks like, if it goes from 0 to pi over 2, when x goes from 0 to a, it looks like our angle theta is this. That is our theta. Okay. Because when, am I right in thinking about that? When x is equal to a, yes, the x coordinate, at any point, if this is my x coordinate, then that's my theta. And when it increases, the theta increases. So then when x is closer to 0 here, the theta is 0. And when x is closer to a, theta is closer to pi over 2. So the angle theta in our case represents this, not with the x-axis, but the angle made with the y-axis. That's our theta. Okay, anyway, I was just trying to get conceptual clarity, of what substitution we are doing. And once we do that, then, we get this in terms of cos theta. And if it is simply cos square theta that you have to integrate, then now this comes in the trigonometric integrals, the previous section. Okay, if it is just the even power of cos square, if there is no odd power of cos or sine, then you do the half angle formula concept, right? Convert cos square to 1 plus cos 2 theta, so it's an odd power, and then you can do the integral. Okay, and substitute, and you get pi AB, which is the area of the ellipse. And when a equal to b, we get pi a square, which is the area of the circle that we know, right? And that's explained here. Okay, moving on. There are some notes here. Because the integral is a definite integral, by the way, so in the first example we had done in the previous video, we had to convert back theta in terms of x, and we did the triangle for that and all that concept. But we didn't bother to do all that here because we are doing definite integral. And we already knew the theta limits. When we converted the integral, we also converted the theta, the limits of theta as well. And so we could be done with that. Okay. All right. One more example. And I hope by this time you are conceptually at least feeling comfortable how this has to be done now, right? You see x square plus 4. So your mind, and there is a square under root sign. Okay. First you check that, you definitely need trigonometric substitution. Like it's not possible to do it without trig. Okay. You have to confirm that. And to confirm that, you notice if you take u equals x square plus 4, which is under the root, du will be 2x dx. Okay, but the problem is you have 1 over x square here. Try. Okay, you should try. Okay, no other substitution is going to work. If you think somehow, if I take u as 1 over x, so du would be, minus 1 over x square dx. Okay, but what are you going to do with this under root x square plus 4 with u as 1 over x, right? So we exhaust all possibilities, and we guarantee that only trig substitution can help here. Okay, then you think x square plus 4, so the Pythagorean identity is 1 plus tan square theta, because of the plus sign there. Okay, and naturally you let x equals 2 tan theta because there is 4 there. So when you square it, you'll get x square would be 4 tan square theta, and you can factor that out 4 here. You get that. Okay, now you substitute back, dx, by the way, x is tan theta, so dx would be, x is 2 tan theta, so dx is 2 sec square theta d theta, and you make all the substitutions here. What do I get? Sec theta over tan square theta. Okay, not easily for me to process that, so convert it in terms of cos and sine. Always, the go-to method is to convert it in terms of sine and cos. And that gives you cos theta over sine square theta, and that should be doable. Now our mind should trigger, one more substitution. Okay, now u equal to sine theta, du is cos theta d theta, right? So that takes care of the integral, and at the end you get minus cosec theta over 4 plus c. Then the triangle method, okay? We set x equals to tan theta, right? So take the theta here, tan theta is x over 2. So x here, 2 here, opposite by adjacent. And hypotenuse should be under root x square plus 4, under root a square plus b square, Pythagoras theorem. And that takes care of cosec theta. Cosec theta is hypotenuse over opposite. Okay, so under root x square plus 4 over x. I guess, yeah, that's what is given here. And you get that. Okay. And there is one more problem where we'll again use the trigonometric substitution, but at the end, once we get the answer, there is one more step we can simplify, which I will explain here. Okay. Firstly, you see x square minus a square. So naturally, you have to think of the replacing x with something, right? So the identity that comes to mind is x square theta minus 1, because it's x square minus a square. So that's what we do, a sec theta, now the derivative of that, okay, by the way, dx would be a sec theta tan theta d theta, right? You convert x square minus a square a tan theta, and dx is x sec theta tan theta. You plug in all that, you're left with just sec theta, and there is no choice other than to recollect this, trigonometric integral. Okay. And once you do that, now you have to write that, using the triangle sec theta plus tan theta, sec theta plus tan theta. And if you take a as common denominator and use the logarithmic identity, ln x over y is what? Ln x minus ln y, right? You get minus ln a, but ln a is a constant. Okay, so this is what I was saying. Even after you do the substitute back in terms of the original variable, sometimes it is possible to simplify it a bit. Okay, instead of leaving at fractions like that, if you take a as common denominator and use this logarithmic identity, you can separate the ln a part, which is constant. So only this part remains as a function, which is better than having a fraction earlier, right? And you get that, okay, plus some constant. Okay. Now I'm going to just slide over some slides and the remaining problems that are solved here. And if there is any concept to explain, I will explain. It says we can do the same thing with hyperbolic functions, which we are not doing. Okay, so I'll skip that. That is all talking the same thing. Okay, here. You're doing this definite integral. Okay, and these are your functions. So the question is, what kind of substitution is going to help you, right? So this is a square plus b square type. So I somehow know it has to be 1 plus tan square theta equals sec square theta, right? That should work. So it has to be x equal to something tan theta, some question mark tan theta. Okay. At the outset, when I look at it, I should be able to say that. But what tan theta? Because if I simply say tan theta, it's going to be 4 tan square theta plus 9. If I said 3 tan theta, it will be 4 times 9, 10, 36 tan square theta plus 9, right? So I have to take it in such a way that it gives you exactly, the denominator becomes exactly a constant. At the end of it, it should become some constant times 1 plus tan square theta, right? Two ways, okay? One, let me see whichever you see, whichever you feel comfortable. One is if you can think ahead about numbers, and especially if you are good with this kind of manipulating the numbers, you'll notice that you should take x as direct answer. Okay, I'm telling you, this would be direct if you can see it. 3 over 2 tan theta. Why? Because when you square that 3 over 2, you are going to get 9 over 4. And the 4 will cancel with 4, and you have 9 tan square theta, which will go with plus 9. If you can see it, that's the simplest way. Okay. All right. Another way would be take 4 another, and in this trick you can always use. Okay, if it doesn't work like that, make sure that you factor out constant, so you have only x square in the substitution level. Okay, if you factor out 4, you get x square plus 9 over 4, right? To get the plus 9 inside, I'm only talking about the inner function here. Okay, then you can see that because you see this as 9 over 4, which is 3 over 2 squared. So now you know that x has to be 3 over 2 tan theta. Okay, somehow you have to see that. And once you see that, you make the substitution. X equals 3 over 2 tan theta. Dx will be 3 over 2 sec square theta d theta. You put that here, you get that. You write everything in terms of tan and sec. Okay, that's all the calculation work. And by the way, the limits are also changed. And when you are doing definite integral, it looks to me changing the limits. No, we have talked about this earlier also. You can either change the limits now or not change the limits now, just do the definite integral. At the end, get everything back in terms of original variable, which is x here, and use the original limits. But looks to me that in this kind of situations, that might increase the work slightly. If you can easily convert the limits now itself, why not do it? Then you don't have to get the theta back in terms of x, which we know requires us to construct the triangle and substitutions. There is a lot of work involved there. So convert the limits now itself. And that's generally easy because of the kind of substitutions we do. X is 3 over 2 tan theta. And the limits of x are 0 and 3 root 3 over 2. So you are going to replace that. If you plug in x equal to 0, you get tan theta equal to 0. And then you get theta equal to 0. If you replace x equals 3 root 3 over 2 equals 3 over 2 tan theta, you get tan theta equals root 3. And that is 60 degree, which is pi over 3. And your limits are from 0 to pi over 3 as it is given here. Here, 0 to pi over 3. Okay. All right. With that, and you change the limits, everything in terms of sec and tan. That's not helpful. Change in terms of sine and cos. You notice your cube here, so you know what to do, right? You are going to take that sine theta out, and the remaining will be sine square theta. That is 1 minus cos square theta, cos square theta. So with u equal to sine theta, u equal to cos theta, sorry, everything will work out. Okay. Again, we change the limits, by the way. You notice that, okay? Second time, because now you are converting, another substitution in terms of u. So theta limits are now changed to u limits, 1 to 1 over 2, and we're done. Finally, we do the integral. Okay. I think that is the end of the slides here. Of course, work on the homework problems and let me know, ask me questions when you go to class. In the next video, I will work on the next topic. Okay, 7.4. I think we are doing some more, on integration, some techniques of integration, some combinations and stuff like that. See you until then.